Requirements for equilibrium. Requirements as a general requirement for equilibrium, we postulate that a system is in equilibrium where there is no possibility that it can do any work when it is isolated from its surrounding. We postulate that a system is in equilibrium when there is no possibility that it can do any work when it is isolated from its surrounding. In applying this criterion, it is helpful to divide the system into two or more subsystems and consider the possibility of doing work by any conceivable interaction between these two subsystems. For example, in this picture, a system has been divided into two subsystems, subsystem 1 and subsystem 2. And also an engine of any conceivable variety placed between these two subsystems, this engine. A system may be so defined as to include the immediate surrounding. In this case, we can let the immediate surrounding be a subsystem and thus consider the general case of the equilibrium between a system and its surrounding. The first requirement for equilibrium is that the two subsystems has the same temperature. The first requirement for equilibrium is that the two subsystems have the same temperature. Otherwise, we could separate a heat engine between the two systems and do work. We could operate a heat engine between the two systems and do work. Thus, we conclude that one requirement for equilibrium is that a system must be at a uniform temperature to be in equilibrium. It is also evident that there must be no balanced mechanical force between the two systems. No unbalanced mechanical forces between the two systems. Or else one could operate a turbine or piston engine between the two systems and do work. A turbine or piston engine between the two systems and do work. We would like to establish general criteria for equilibrium that would apply to all simple compressible substances, including those that undergo chemical reaction. We will find the Gibbs function is a particularly significant. The Gibbs function is a particularly significant property in defining the criteria for equilibrium. Gibbs function. We said that G equals to H minus Ts. Let us first consider a qualitative example for illustrate this point. Consider a natural gas well that is 1 kilometer deep, as shown in the picture. Consider this picture for an example. 1 kilometer deep natural gas and let us assume that the temperature of the gas is constant throughout the gas well. The temperature throughout the gas. Suppose we have analyzed the composition of the gas at the top of the well and we would like to know the composition of the gas at the bottom of the well. Furthermore, let us assume that the equilibrium condition prevailed in the well. If this is true, we would expect that an engine such as that shown in this picture, which operates on the basis of the pressure and composition change with the elevation and does not involve combustion, would not be capable of doing work. If we consider a steady state process, for a control volume around this engine, the reversible work for the change of state from I to E can be expressed as this relation. Reversible work M dot I T0 SI M dot E Furthermore, since Ti equals to Te T0 this reduces to the form of Gibbs function W reversible M dot I Gi where these quantities are Gibbs function. However, for the equilibrium, Gi and the requirement For equilibrium in level between two levels that are a distance dz apart would be at a distance dz at temperature constant equals to 0. In constant to a deep gas well, most of the systems that we consider are of such size that delta Z is negligibly small, and therefore we consider the pressure to be uniform throughout. This leads to the general statement of equilibrium that applies to simple compressible substance that may undergo a change in chemical composition, namely that at equilibrium so delta Z negligibly small, so the chemical composition general statement for the equilibrium to simple compressible substances that may undergo a change in chemical composition namely that at equilibrium is that delta G dg of G and P. In the case of a chemical reaction, it is helpful to think of the equilibrium state as the state in which the Gibbs function is minimum. The Gibbs function is a minimum. For example, consider a control mass consisting initially of Na moles of substance A and Nb moles of substance B, which reacts in accordance with the relation let the reaction take place at constant pressure and temperature. If we plot G for this control mass as a function of Na, the number of mole of A percent, we would have a curve as shown in this picture. At the minimum point on the curve, dGTP equals to 0, this point. And this will be the equilibrium composition for this system at the given temperature and pressure. The subject of chemical equilibrium will be developed further in the next section 16.4. The next section is 16.4, 16.2, equilibrium between two phases of a pure substance.